Hello students, now let's move on to next theorem. If f belongs to R of alpha and g belongs to R of alpha on closed interval ab, then f plus g also belongs to R of alpha. That is, if the function f and g belongs to R of alpha, that is, if f and g are Riemann-Stieltjes integrable on closed interval AB, then f plus g is also Riemann-Stieltjes integrable. Okay, that is what we need to prove in the first part of the theorem. And also in the second part, integral a to b f plus g d alpha is equal to integral a to b f d alpha plus integral a to b g d alpha. So this is what we need to prove in the second part of the theorem. Okay, so now let's quickly get into the proof. Given f belongs to R of alpha, g belongs to R of alpha on closed interval ab, and let h is equal to f plus g. So I am naming this as some function h. Okay, so now h is equal to f plus g, and it implies h is bounded. Why? Because f is bounded, g is bounded. Why f and g are bounded? Because they are Riemann-Stieltjes integrable. So in one of the note in previous video, I have already mentioned that if a function is Riemann-Stieltjes integrable, then it is bounded. So the necessary condition for the function f to be Riemann-Stieltjes integrable is it should be bounded. Okay, so here since f and g are Riemann-Stieltjes integrable, f and g are bounded. And if f and g are bounded, h, which is equal to f plus g, is also bounded. Okay, so here let P be any partition of closed interval AB such that P is equal to x0, x1, x2, etc. up to xn, where x0 equal to A and xn equal to B. And since this f, g, h are all bounded, its infimum and supremum exists. So let mi dash is mi double dash mi be the infimum of fi, g and h. So let this be the infimum of f, and this be the infimum of g, and this be the infimum of h respectively on this subinterval. Okay, let mi dash mi double dash mi be the supremum of f, g and h respectively on the same subinterval xi minus 1 comma xi. Okay, and clearly I can write mi dash plus mi double dash is less than or equal to mi. See here I can use this. Okay, see here I can use this and write infimum of f plus g is greater than or equal to infimum of f plus infimum of g, or infimum of f plus infimum of g is less than or equal to infimum of f plus g. So here I can use this and write mi dash plus mi double dash less than or equal to mi. And similarly I can use this and write this mi less than or equal to mi dash plus capital Mi double dash. So, and for each infimum and supremum, this inequality holds. Small mi less than or equal to capital Mi. So, in this way, I will relate all these things. Okay, Mi dash plus Mi double dash less than or equal to Mi, less than or equal to capital Mi, less than or equal to capital Mi dash plus capital Mi double dash. Okay, now what I will do, I will multiply throughout by delta alpha I, and I will sum up from I equal to 1 to n. Okay, so now I will get like this, and I will split these two. So I will get like this, and here also I will split these two, and here I will get like this. And this is nothing but the definition of lower sum. Okay, and I have written L of p comma f comma alpha, since this mi dash is the infimum of the function f in the interval xi minus 1 comma xi, and here mi double dash, see here summation I equal to 1 1 to n mi double dash delta alpha I according to the lower sum definition, it's equal to L of p comma g comma alpha. Okay, so here I have written g because mi double dash is the infimum of the function g in the interval xi minus 1 comma xi. Okay, and this is, let's see, I have written all those things respectively. Okay, L of p comma h comma alpha, u of p comma h comma alpha, u of p comma f comma alpha, u of p comma g comma alpha. Okay, and here I can write this u of p comma h comma alpha minus L of p comma h comma alpha less than or equal to this minus this. So at last you will get like this. Okay, u of p comma h comma alpha minus L of p comma h comma alpha less than or equal to u of p comma f comma alpha minus L of p comma f comma alpha plus u of p comma g comma alpha minus L of p comma g comma alpha. See here, this is for any partition. Okay, this equation, see here, this equation holds true for any partition P. Okay, so and also since f belongs to R of alpha, g belongs to R of alpha, for any epsilon positive there exist partitions P1 and P2 of closed interval a comma b such that u of p1 comma f comma alpha minus L of p1 comma f comma alpha less than epsilon by 2. Okay, see here why we use epsilon by 2 is you will come to know in the upcoming steps. Okay, see there will be sum of 2 and if I write epsilon by 2 then epsilon by 2 plus epsilon by 2 will become epsilon. See if I have sum of 3 then I will take that as epsilon by 3. Okay, so similarly for u of p2 comma g comma alpha minus L of p2 comma g comma alpha less than epsilon by 2. And now I will take the common refinement p star of p1 and p2. So I will take p star equal to p1 union p2 which becomes the common refinement of p1 and p2. So this holds for p star also. See here in previous theorem we have learned this is less than or equal to this, and since this is less than epsilon by 2 I have written this less than epsilon by 2. Okay, and this also less than epsilon by 2. Why? Because this is less than or equal to this first, and since this is less than epsilon by 2 I have written this less than epsilon by 2, and similarly this holds for this also. Okay, so I have written u of p star comma g comma alpha minus L of p star comma g comma alpha less than epsilon by 2. And now using this 1 and 2, using this equation and this equation, we have, okay, see from 1 and 2 I have u of p star comma h comma alpha minus L of p star comma h comma alpha less than or equal to, see you just don't worry about this step. Okay, see I have written that directly. Okay, see here I have used this. See here I have again written this as equation 1. Okay, so I have directly used this. Okay, and since this is true for any partition P, now it must be true for the partition P star also. Okay, so here u of p star comma h comma alpha minus L of p star comma h comma alpha less than or equal to u of p star comma f comma alpha plus u of p star comma g comma alpha minus L of p star comma f comma alpha minus L of p star comma g comma alpha. And from equation 2 we have this minus this less than epsilon by 2 and this minus this less than epsilon by 2. So totally I have this thing less than epsilon, and which implies H also belongs to R of alpha on closed interval AB using the condition of integrability. See, I have the difference of upper sum and lower sum less than epsilon with respect to the function f and with respect to the partition P star. So I can write H belongs to R of alpha, or H is Riemann-Stieltjes integrable on closed interval AB. H is nothing but the sum of f and g. So if H belongs to R of alpha, then obviously f plus g also belongs to order of alpha on closed interval AB. Okay. Now, let's move on to the second part of the theorem. Here, we need to prove that integral a to b f plus gd alpha is equal to integral a to b f d alpha plus integral a to b gd alpha. See here, in place of f plus g, I have taken that as h. Okay, so we have a plus integral a to b hd alpha is equal to integral a to b fd alpha plus integral a to b gd alpha. So we need to prove this. Okay, and from 1 we have, see, I have taken the part of 1. Okay, so u of p comma h comma alpha less than or equal to u of p comma f comma alpha plus u of p comma g comma alpha. So this is from equation 1. Okay, now taking the infimum of upper sums. So if I take the infimum of these things, I have integral a to b bar, that is the upper Riemann integral. Okay, so I can write this upper Riemann integral of h, and here upper Riemann integral of f and g here. Okay, so if we take the infimum of upper sums, that is nothing but the definition of upper Riemann integral. Okay, so now taking the infimum of upper sums, we get the upper Riemann integral. Okay, so here of h, here of f, and here of g. Also, if I take the second part of equation 1, I have L of p comma h comma alpha greater than or equal to L of p comma f comma alpha plus L of p comma g comma alpha. Now taking the supremum of lower sums, according to the definition of lower Riemann integral, I have this integral a to b, that is lower Riemann integral hd alpha with this f and g here similarly. Okay, so I will name this as equation 3 and I will name this as equation 4. Okay, and we know that f belongs to R of alpha and g belongs to R of alpha. If so, then I can write this as integral a to b f d alpha. Why? Because f belongs to R of alpha. And similarly, I can write this as integral a to b gd alpha. Why? Because g belongs to R of alpha. And similarly here also, I can write this lower Riemann integral as integral a to b fd alpha, and similarly here. So 3 implies this one and 4 implies this one. Okay, and also in the first part of the theorem, we have proved that h also belongs to alpha. Okay, so now if I substitute all these things here now, integral a to b hd alpha less than or equal to this thing, and integral a to b hd alpha greater than or equal to this thing. So since h also belongs to R of alpha, I can write this upper Riemann integral as integral a to b hd alpha. Okay, similarly in place of lower Riemann integral, simply I can write integral a to b hd alpha. Why? Because h belongs to R of alpha or f plus g belongs to R of alpha, as we have proved this in the first part of the theorem. Okay, I am using that. So from this and this, I can write at last this is equal to integral a to b fd alpha plus integral a to b gd alpha. So this is what we need to prove. So this is the proof of the second part of the theorem. Thank you.